In today's video, I am going to explain you how to write VHDL code of universal shift register with serial in serial out operation for left shift, for right shift, and parallel in parallel out modes, and synthesize and simulate the same using XILINX software suite 14.7. Before moving towards the code, first we should know what is universal shift register. Universal shift register is a register that can store the data and shifts the data towards the right and left along with parallel load capability. Is known as the universal shift register. For 4-bit, we require the 4 flip-flops, and for select modes or control modes we require 4:1 mux. This is the operation table of the 4-bit universal shift register. We have 4 modes. For each mode there is a one operation. For 00, no change. For 01, shift right. For 10, shift left. And for 11, parallel loading operation. One by one we can see how the data is shifted towards the left and right. So here, consider this figure. You can see my initial data is 000, and for first falling, or we can say for first, you can choose positive edge triggered or negative edge triggered. If negative edge triggered is there, falling edge, and for positive edge trigger there is a rising edge. So for first falling or rising edge, if my input data is at the MSB bit is 1, then you can see first one, my input data is loaded at the MSB bit and other bits are shifted towards right. For second clock pulse, again my input is 1 and my data is shifted to a right side. Again 1, you can see my data is shifted towards right side. So finally for fourth clock pulse, at the output side I will get 111, that is 4 bits are shifted towards the right side. And for, you can see, for the shift left operation, I will show you. For shift left operation, you can see here in this figure, for shift left operation we have to give the input bit at the LSB bit, that means least significant bit. So if my input bit is 0, so my 0 is loading at the LSB position and other bits are shifted to the left side. So how many clock pulses are required? That is the 4 for the 4-bit shifting operation. And about parallel loading operation, so parallel loading operation, parallel load means to load all the flip-flops of a register at a one time, and we get the all the 4 bits at the output side. Now moving towards the VHDL code, you can see this is my VHDL code for the 4-bit shift register. So every shift register, there is 3 parts for VHDL code, that is library files, entity part, and architecture part. So library files we should include in the program to use the library and packages required for the program. So library files always contains the packages, and the packages which can contains the user defined data types and constants. So packages and libraries serves as a repositories for functions and procedures and data types. So library IEEE standard logic 1164.all, these are the packages and libraries which serves as a repositories for function, procedures, and data types. Now use IEEE standard logic arith.all is a library package, another library package, and which specifies the signed and unsigned data types and related arithmetic and comparison operation. That means it allows the arithmetic operations. And the standard logic unsigned.all is the library. This library extends the standard logic arith library to handle the standard logic vector values as unsigned integers. So these are the library files we should include in the program. Then there is a most important point, that is the entity. So entity is basically the inputs and output signals of your digital circuit. How many inputs are there and outputs are there in your digital circuit? That's what about your entity, that means input and output. So you can see here for data in we have D in, which is 4-bit, then clock we require because we are using flip-flop, then reset for the resetting the machine, then circuit, then S is the for select modes, we have 2 select lines, that's why 1 down to 0, then D out is our output. So here 3 down to 0 is 4 bit and 1 down to 0 because we have to select inputs, that's why it's a 1 down to 0. And standard logic means 1 bit, and for standard logic vector is used for the several bits more than 1 bit. So here this is the entity. Architecture means the internal structure or the operation of your digital circuit. You can write architecture using the three modeling styles: behavioral, data flow, and structural. I'm going to use the behavioral modeling style here, and you can see here this is architecture is begin here, and I have used the process statement because I'm going to write the behavioral program using behavioral modeling style. So in process statement you can see there is a clock and reset. So what is this clock and reset? This is the sensitivity list. Sensitivity list means the sensitive inputs, that means output is very sensitive to these inputs. Here again, here after process statement begin, program started. If reset is equal to 1, d out is equal to 0. Obviously reset is done. Next, else if clock tick event and clock is equal to 1. This clock is equal to 1, we know we require the clock signal, and clock tick event means our flip flop is edge trigger, that means rising edge we have to give, that means clock tick event and clock is equal to 1, that means your clock is equal to 1 and we have give the rising edge clock pulse. Now here after this, what is this? MSB is equal to D in 3. We have to define what is MSB and what is LSB in. So MSB in our most significant bit, that's why D in is equal to 3, and LSB in our less significant bit, that's why D in is equal to 0. Now here case statement is started. When 0 0, D out is equal to D out, that means no change. When 0 1, D out is equal to MSB and D out 3 down to 0. When 1 0, D out is equal to D out 2 down to 0 and LSBN, and for 1 0 0, D out is equal to D in, that means parallel loading operation, and when others, D out is equal to 0. So you can see this line, that means for shift right operation D out is equal to MSB in and concatenated with the D out 3 down to 0. That means load first MSB bit and shift this MSB bit towards right side. That means our first bit is loaded at the MSB position and other bits shifted to right side. This is 10 is for left shift operation. That means load first LSB bit and shift data towards the left side. And this is the parallel loading operation. That means if we load the 4-bit data flip flop at flip flop once, means sorry, not once, at a time, then we will get this data at a time at the output, and with the others, that is D out is equal to 0 0. End case, and if end process and end behavioral. So this is our VHDL code for the flip flop. Now we will see exact process how to write the VHDL code in the XILINX software, and what is the whole process to simulate and synthesis. So first, new project, give some name, for example shift universal. Okay, now next, here you can select the family and device. I have selected Spartan 3 XE3 S400, and you can select preferred language VHDL or Verilog. Next, finish. Now here your shift universal file is, your project is created. Now click on that new source. Now we have to declare VHDL model. Again give the name, suppose universal, and next, and here you can define your input output. So we have D in, then we have clock, then we have reset, then we have select mode, and we have D out. So D in is our input data, which is a 4-bit, that's why I have selected bus, and it's a 3 down to 0. Then clock is a in standard logic, reset is the in standard logic, S is our mode select, that is 1 down to 0. D out is our in out, and which is again 3 down to 0. We have selected here, you can see in out, because this is the for reading and writing both we are going to use this d out. That's why I have given the in out here. You can see in this program again, here d out is in out, that means for reading as well as the writing purpose. So now come to the this XILINX window. So this is D in, clock reset, SD out. Now just next again you can check here, clock reset, select D out and D in, finish. Now our, you can see here in program our entity is created, library files also there, that is use IEEE standard logic 1164, and this is our entity D in, clock reset, then there is S and day out and entities. Now entity is ready. We have to write the program in architectural part after begin. So we have already our code that is here. So just copy from process and just copy it and paste it here in your code. So I just paste it here, and you can check again if reset is equal to other things. And then we require the other library files as well, that is for arithmetic operation. Copy, these two files are required. So just copy it again, go to the XILINX window and just go to library section, library files section, and just paste it here. So our program is now ready, that is library files, entity and architecture. Now you have to save again, then go to the synthesize part and you can do the check syntax. Now here you can see 57, line 57, undefined symbol. So you can see I have used in my program LSBN and MSBN, and MSBN, but I have to declare the signal. So see in the program where are these two signals are declared. So you can see these signals are declared in here. Before begin we have to declare these two signals. So just go to the program here and just declare these two signal. That is, what are these two signal? That is MSB in, and just copy it here, copy it, MSB in, just again copy LSB in, and these are the type standard logic. Copy, okay, and the semicolon. So here you can give here begin. Now save again and start check syntax. Again line 46, what is the error? Unexpected identifier. So we can see MSB and LSB in standard logic vector. Now just open our program and see what is the issue. MSB in and LSB in. So here we have to include the signal MSB in, LSB in, which is type of standard logic. Now save and again check syntax. Again you can see line 53 we have the error. So just check what is that error. So here 100, that is the error. So just remove it, save again and check syntax. So here no errors are there, check syntax completed. Now synthesize. Now synthesis is completed. So you can see the view RTL schematic. Okay, so here your RTL schematic, that is register transfer level schematic. Now we have to simulate the model. So first go to the file and we have to create first test bench code. So select VHDL test bench, give test bench waveform, and next finish. Now you can see our test bench code is generated for the 4-bit universal shift register. Here you can see the test bench code. Now we have to simulate the model. So just click on simulation, click on your file and simulate behavioral model. Okay, so output window, simulation window is here. Now first, for universal shift register we have to give the clock pulse. So go to the clock pulse, right click, force clock, leading edge is 1 for positive edge triggered, then trailing edge is 0, and give some time period. Suppose this is my time period. Apply, okay. And for reset operation, give the force constant is, for reset value is 1. Apply, okay. Now just run for the specified time. So you can see here your register is resetted. That is, we have at the output we have got the 00 value. Now we'll see first the parallel loading operation. So for parallel loading, our select mode is 111. Apply, okay. And give the data here 4 bits at a time, that is 1000. Suppose, apply, okay. And we have to do the reset again. Value is 0 because I already done the reset process. Now just run for the specified time. You can see we have give the 100 data and mode is 111, and see the output. So for next clock pulse, for first clock pulse, you can see here our data is loaded, and for second clock pulse we have get the same 4-bit data at the output, that is the parallel loading operation. Now we'll see the left shift operation and the right shift operation. So again we have relaunch, then you can see here again give the clock is equal to 1 because we want to apply the clock pulse and also the positive edge triggered clock pulse. That means leading edge is 1, trailing edge is again 0. Give some time period 1 2 3 4 5 6. Again apply and okay. Now again reset, force constant is 0, sorry 1. Apply, okay. Now run for the specified time. You can see reset is done. Now just apply for left shift operation. Our mode is 1 0, and apply, okay. And reset, force constant, reset is 0 now. Apply, okay. And give the LSB bit, that is here just I'm giving the 1 at LSB bit, and apply and okay. Now run for the specified time. You can see we have given the LSB bit 1 at the LSB position, and mode is 10. Now run for the specified target, run for the specified time. You can see our this LSB bit is shifted towards left. That means first it is here, for second clock pulse it is here, third clock pulse it is here, and for the fourth clock pulse our bit is shifted towards the left in 4 clock pulse. We required the 4 clock pulse, you can see here. So this is the left shift operation. Now we'll see the right shift operation. Again I'm going to relaunch it. Again give the clock, that is clock is equal to 1, and clock tick event, that means right click on that, force clock, again 1 0, give some time period, apply, okay. Then again reset is equal to 1 to reset, apply, okay. And run for the specified time. Reset is done. Now select your mode of operation. I want to do right shift, that is mode of operation is 0 1. Apply, okay. Reset is 0, reset is 0, apply, okay. And here for right shift operation I am going to give the data 1 at the MSB bit, that is 1. Apply, OK, and run for the specified time. You can see in the figure my mode is 0 1. I have given the MSB bit 1. Again run, second clock pulse, third clock pulse. You can see my data is shifted towards right side. First bit is here MSB, then here 110, and finally 111. So my data is shifted in 4 clock pulses to the right side for 4 bits. So this is all about the 4-bit universal shift register with left shift, right shift and parallel loading operation. Thank you so much.